Good afternoon everyone, welcome to Get Academy Global. So in the last class of this EMT crash course, we discussed about the Coulomb's law and electric field intensity. So as I told you in the last class that I am going to discuss today about the charge distribution and the electric field intensity due to the different charge distribution. Okay. So let's start with that charge distribution. So in the charge distribution, actually what we study is the charge is not always present in the form of point. Before this topic we discussed about the point charges. So it is not necessary that the charges will be present in the form of point. It may present in the line, along the line, it may present on the surface, it may present on the volume. So we have to consider all that charge configurations, and for all those charge configuration we have to find the electric field. Okay. So we are saying that we will have a point charge, say like this. If it is a point charge, say Q, then because this is a point charge, so electric field is fixed for this, and the electric field we have calculated yesterday, that is KQ by R square and AR cap. Okay. Now it is also possible that the charges might present in the form of line. So suppose this is the line and the charges will be present here in the form of line. So this is the charges present. So when the charges are distributed in the line, when the charges are distributed in the line, it is defined by line charge density. Okay. So it is defined by line charge density. Line charge density is denoted by ρL and its unit is Coulomb per meter, So if you want to calculate the charge in certain part of this line, like if you want to calculate the charge in this part of the line, say dl, in this small portion of the line, if you want to calculate the charge, how can you calculate? In this small portion of the line, if you want to calculate the charge, so how can we calculate? So as you can see that this line charge density is nothing but the charge per unit length. So that means if you will multiply with the length, you will get the charge. As you can see that the unit also Coulomb per meter, that means you have to multiply it by the meter, and the meter, the dimension will be length. So if you want to find the charge in certain part of the line, you have to multiply with that length. So in this small portion, if you want to find the charge, so let us say this is dq and this will be ρL into that small length, which is dl, ρL into dl. This is the charge present in this small part. But if you want to find the total charge present in the line, so this total charge is Q into integration over the length L and ρL into dl. So this is the charge present, total charge present in the line. Now what is the electric field for this? So the electric field, as we have written here, the electric field is KQ by R square into AR cap. So Q is the total charge of this point. So whatever will be the charge here, the point charge is directly written there, because that is actually a total charge at that point. Now if you want to write the electric field for this line charge, so this is written as, according to this formula, we will write E, vector E is equal to, this Q should be replaced by this one. So this is K times integration over the length rho L into dl upon R square into AR cap. Just you need to replace the total charge Q and you will get the formula for electric field for a line charge. So when you derive electric field for any line charge configuration, whether it is a circular in shape, whether it is a straight, or whether it is a finite length or infinite length, you have to apply this formula to calculate electric field because of the line charge configuration. Okay. Yes, Ishwara, so the potential inside the sphere depends, it is constant if you are talking about the conducting sphere. So if you are talking about the conducting sphere, it is a constant, okay, because the electric field is the gradient of potential, and when the potential is constant, the electric field will be 0 inside the sphere. So if you are talking about the conducting sphere, then the voltage remains constant inside the sphere. Now, it is also possible that the charges may distributed on the surface also. So suppose this is the surface, that means a plane. So suppose this is a plane in which the charges are distributed. So the charges are distributed like this. So the charges are present like this. When the charges are present in the plane or any surface, then it is defined by rho s, and it is called surface charge density. It is called surface charge density, and the surface charge density is defined as charge per unit area. So because it is defined as the charge per unit area, its unit is coulomb per meter square. Its unit is coulomb per meter square. Coulomb per meter square. So if you want to calculate the charges present in this region, suppose you want to calculate the charges present in this region, in this surface like this. So suppose I will say that ds is the surface in which you want to calculate the charge. So as we can see that this charge per unit area, that means you have to multiply it with the area. So when you multiply it with the area, you will get the charges present in that small area. In this particular surface you want to calculate the charge, so for that you have to multiply it with the area of that surface. So this is ds, rho s into ds. Now again if you want to write the total charges present in this whole surface, so you have to integrate it over the surface and the rho s into ds. This will be the charge present. Now again, if you want to write the electric field, because you have got the total charge, you can write the equation of electric field at any distance r from this surface. So suppose you want to calculate the electric field at any point P, which is at distance r from this differential surface, then the electric field will be given by, then this electric field will be E is equal to K into, the charge Q is replaced by integration over the surface and rho s into ds divided by r square into ar cap. So electric field is always along the line joining between them. So electric field is along the line joining, so the electric field will be in this direction. Okay, so the electric field will be in this direction. So along the line joining from the surface to the point of interest. Now suppose you want to calculate the charge over a volume. Suppose you are having a volume like this, suppose the charges are present in this volume in this way. Now let's make some volume, small elemental volume. This is given as dV. Because the charges are distributed in the volume, whenever the charges are distributed in the volume, it is defined by rho v, which is called volume charge density, which is defined as volume charge density. And it is nothing but charge per unit volume, which is given by Coulomb per meter cube. Charge per unit volume, and it is given by Coulomb per meter cube. So if you want to calculate the charges present in the volume, the charges present in this volume, it is given by dq is equal to rho v into dv. You have to multiply it by volume. So we are multiplying it with the volume of this particular complete surface, closed surface. If you want to calculate the charges in this volume only, then you have to multiply with that volume. And if you want to calculate the total charge present in the whole volume, so for that you have to integrate it over the volume. So this is rho v into dv. Now similarly, the electric field expression, how can you write? So the expression for the electric field will be K into integration over the volume, the charge is replaced by integration over the volume rho v into dv divided by r square and ar cap. So this is the electric field due to the volume charge. Hello Rushikesh, good afternoon. Tarun, for EC, electrostatic and magnetostatic are in syllabus, but it is not mentioned, it will be present indirectly. So I will not recommend to leave it, but if you are not having time, then the chapters that can be left in the subject EMT are electrostatic and magnetostatic. So that can be uh, kept in the least priority in your study. Okay. Okay, Tarun. You can keep it in your least priority, but you should not ignore it, because there is a possibility that they will ask the question from that particular topic also, because it includes the Maxwell equation. So they can ask question from the Maxwell equation, and if they do ask question from the Maxwell equation, they might be asking about the Gauss's law, Ampere's law. So if you ignore it and if they ask question, then you will ask them for mark to all, but they will not give. So I will recommend you to study, but if you are having the time. If you are not having the time, you can leave it for now. Yes, Tarun, then if you have watched my all the videos from the electrostatic and magnetostatic, so that is sufficient. No need to study more than that. Okay, so that topics I have covered is already sufficient. So there is no need for extra topics to be studied. Okay, so we have completed up to this part. Now we have to calculate the electric field because of the different charge configurations. Like we will calculate for the electric field, we will calculate electric field due to first infinite long line charge, second circular ring, third circular disc, fourth infinite charge sheet. Okay, so we have to study the electric field intensity because of all these four charge configuration. Okay, so you should study this part at least for the practice, and they can ask the question from this topic. So one by one we will discuss each configuration, and we will see what is the electric field because of these charge configurations, and after that we will solve few questions related to these topics. Okay. So first topic is electric field due to infinite charge sheet. So in the infinite charge sheet, what will happen? Suppose we will be having a charge, infinite line charge like this. This is the infinite long line charge. Okay. So the charges are present. So the charges are present here. We have kept it in the along the z direction. Okay. We have kept it along the z direction. So this is the z axis. So this is the z axis. We have kept the line charge along the z axis, and the charges are present here. Like this. If the charges are present throughout the line, and we want to calculate the electric field at point P, electric field at point P, say this is the point P. This point P is having some coordinate x, y, z, say. Now if you want to calculate the electric field at point P, because this is the infinite long line charge, so you will apply the formula for the line charge. Okay, so what was the formula for the electric field for a line charge? It is K into integration over the length rho L into dl divided by r square into AR cap. So if you want to calculate the electric field because of the line charge, any kind of line charge, whether it is a finite, whether it is a infinite, we don't need to study about the finite length line charge. We are only concerned about the infinite long line charge. So first of all, you have to select the dl. If you want to write the electric field, you have to select the dl. So let's consider the differential length somewhere here. So suppose this is the length dl you have selected, and because this is the line charge, it will be defined by the line charge density rho L. So that is for sure. Okay, so that is very obvious also. So this is line charge rho L. So the line charge density of this line charge is given, which is rho L, and it is in coulomb per meter. That is okay. Now we want to calculate the electric field at point P, and for that we have to select the differential length that I have denoted. Anywhere in the line charge you have to take the small length. So we have taken that small length. And now the second is the distance r, because the rho L is already given, K is constant. Now we have to consider this r. The r is the distance from the length, differential length to point of interest. So r is the distance between this length to this point of interest. So we have to join the line. So we have to join the line with, to get the value of r. So this is the value of r. Okay. Now because this line joining and this point of interest is making an angle theta, say, the electric field will always lie in the direction of r. You can see that the electric field lies in the direction of line joining. So we are joining the line in this direction. We are joining the line in this direction. So that means the electric field will be in this direction because of that small length. Because of that small length, the electric field direction will be in this direction. Similarly, if I take the small length just below this point, at the same distance, if I take the small length differential length dl, if I would have taken the differential length here, because we have to consider all the length. So this small dl will make a complete length, infinite length. So if the electric field because of this differential length is in this direction, then the electric field because of this differential length will be in this direction. So that is also dE. Okay, because both are having the same distance above and below, so that is why they will make the same angle theta. And when you join the line here, and when you resolve it, this angle will be theta, this angle will also be theta. So when you resolve it, the one component of the electric field will go in the upward direction, that is in the z direction, and another component will go in this direction. For this electric field, if you resolve the component of electric field, one component will go in the z direction, another component will go in this radial direction. And for this electric field dE, that is also making an angle theta. So one component will go in this direction and another component will go in the downward direction. So it will happen for all the possible differential length which is above and below this line, If you will consider the differential length here and at the same distance below this, then also you will join the line, and the direction of electric field will go in this direction and the direction of electric field will go in this direction. And when you resolve it, again the electric field will go in this radial direction and another will be in this direction. So what you can see is all the field lines which are equal and opposite can cancel each other. So it will cancel the electric fields, it will cancel these electric fields, right? And all the electric field components that are in this directions are added together. So the direction of electric field for this infinite long line charge will be in this direction. The z component will cancel each other. Yes, Suryavanshi, there was I think very less question from the EMT in conventional, so I have to check and I will be giving that. Okay, I will be taking the session for the electrical EMT also, if it is possible. If there is a good question, then I will take the session for conventional also, ESC conventional. Okay. So actually it is not important right now, we are more focusing on the gate right now, and you will be having the exam in the July, and after 3 to 4 months, that means in the next year of November and December you will be having the conventional exam. So you will be having the sufficient time to prepare for ESC, and that is why we are not that much focused on this ESC. If there is a good concept which can be helpful for gate also, if it is normal derivation kind of question is asked, so there is no need of taking the session on the conventional paper if there is only derivation kind of thing is asked. If there is a good concept in the question, then definitely I will be discussing it with you on the YouTube live. Okay. If you are facing problem in EMT plane wave, then you can follow the Gate Academy global live session in the evening. Okay, we are having the session in the evening. So what we are getting is the electric field due to the line charge will always lie in this direction. And what is this direction? This direction is nothing but the perpendicular distance from the line charge to point of interest. When we draw the perpendicular line from the line charge to point of interest, say rho, I am representing it by rho. So when you draw the perpendicular line from the line charge to point of interest P, and it is the distance rho, okay, in that direction where you draw the perpendicular line from the charge to point of interest, the electric field will exist. So the electric field due to the infinite long line charge, after whole derivation, I am not discussing the derivation part, but why the direction is taken in this direction rho, that I explained you in this diagram. So whenever the infinite long line charge is given to you, the electric field intensity due to the infinite long line charge is given by rho L into rho L divided by 2 pi epsilon naught rho. This is the magnitude of the electric field, and the direction is in the direction of rho where you draw the perpendicular line. Okay. And in the form of a vector, rho L into vector rho divided by 2 pi epsilon naught rho square. So what is rho? So rho is perpendicular distance from line charge to point of interest. Perpendicular distance from line charge to point of interest, that is the rho. Okay, rho is the perpendicular distance, and the direction in which you draw the perpendicular distance, the electric field will exist. Okay. So the direction in which we draw perpendicular distance, electric field will exist. Okay. Sadia, when you take the class of spherical cylindrical dot cross product of electromagnetic waves, spherical cylindrical dot cross product, Sadia, we have covered in the coordinate system. I think you have not watched it yet. So please watch those videos first. I have already covered the cross product. In electromagnetic wave, there is no need of a cylindrical and spherical cross product. So in electromagnetic wave, we only discuss about the Cartesian coordinate system. So there is no need of cross product of the spherical and coordinate dot cross product in EM waves. So next is electric field intensity due to circular ring. Electric field intensity due to circular ring. So suppose there is a coordinate system. This is the coordinate system. Let us say this is x, this is y, and this is z. Suppose a circular ring, the charge circular ring is placed in z is equal to 0 plane. Suppose a charged circular ring like this, it is placed at z is equal to 0 plane. At z is equal to 0, that is the xy plane, it is placed, and the radius of this circular ring, the radius of this circular ring is say r, okay, and we want to calculate the electric field at any point P which is at height h from the ring, which is at height h from the ring. So the distance from the circular ring, from the center of the circular ring is h. So now we want to calculate the electric field at point P. So again, because you are calculating it for the circular ring, that is nothing but a charged circular ring, the charges are distributed in this surface, in that circular ring like this, and if it is distributed in the ring, so it is defined by the line charge density. It is defined by the line charge density rho L. So if you want to calculate the electric field, again you have to select the differential length, because this is the form of a finite length line charge. If you will be having a finite length, you can make it circle from there. You can make the circle from the finite length line, okay. So it is defined by the line charge density. So if you want to find the electric field, you have to take the differential length again, and if you take the differential length, suppose if you take the differential length here, then this radius, let us represent it by A because the notation is going to be same now. Okay, so radius of the circular ring is A, suppose. Now when you join the line, from the differential length to point of interest, the electric field will exist in this direction. Okay. Similarly, if you will join the line from somewhere here, the electric field will exist in somewhere in this direction. So when we divide it into components, the electric field will go in this direction and above direction, and for this dE, and this is also dE because this is because of that small portion dl. So if it is dl, and the electric field because of this dl will be in this direction, z direction, and in the radial direction. So again this radial direction and this radial direction are opposite to each other, so they will cancel each other. Okay, so they will cancel each other, but all the fields which is going in the z direction are having the same direction. So all are added together and they will give you the electric field in the direction of positive z. So if our point of interest is above the plane, where the circular ring is placed, the electric field will be in the positive z direction. Because it is placed at z is equal to 0, when you will move from the circular ring to point of interest, this is the circular ring, and when you move from the circular ring to point of interest, the direction in which you are moving will give you the direction of electric field. Because this is z is equal to 0, this is z is equal to h, because the point of interest is z is equal to h, 0, 0, h. So you are moving in the positive direction, the electric field will be positive. The direction of the electric field will be positive. And if your point of interest is somewhere here, suppose at q, which is 0, 0 minus h, the electric field will be, the direction of electric field will be negative z, because now this is going in the negative direction. Your point of interest should always be your final point. So whatever will be the charge configuration given to you, you should move from that charge configuration to point of interest. So the direction in which you are moving will give you the direction of electric field. If you are moving in the positive z direction, it will give you the positive z. If you are moving in the negative z direction, the direction of electric field will be negative z. So in this way you have to decide the direction of electric field. Okay, like if you want to calculate electric field because of this, so the direction of electric field will be in this direction and the direction of electric field will be in this direction. But when you resolve it, the electric field will be resolved because of this. This electric field will be resolved in this two direction, and this electric field will be resolved in this direction and in this direction. So again this will cancel each other, and the whole electric field direction is the negative z direction. So in this way you have to decide the direction of electric field. You are a student from BUET, means what is BUET? Gaurav, if you are EC student and you want to watch this electrostatic and magnetostatic, then you can refer the main channel, because in the main channel in the playlist there is already a whole content of electrostatic and magnetostatic are present, and if you can understand Hindi, then that would be more beneficial for you, because the playlist is already available. You can watch the whole video in the single day. So that is up to you. Okay. So if you want to finish the course as soon as possible, and if you are comfortable in Hindi, then you can go to the main channel, and there you will find what are the playlist in the playlist section, and there you will get the content for the electrostatic and magnetostatic. Okay, Sadia. So you are from Bangladesh University of Engineering and Technology, and if you are reading the electromagnetics there, so I think if you have to buy the full course, because here we are just taking the crash course, so that's why I will not be discussing that much in detail. So if you want to derive each and everything, because as you said you are in the third semester, so because you are in third semester, you should take the full course. So that's why you will get the derivation, because you are going to prepare it for your semester exam. So if you are preparing for your semester exam, so the derivation you will need, the derivation part you should understand, and that part you can understand from the from the full course of GATE Academy. That is also present in English for few subjects. Okay, so now what we are saying that what is the electric field now? So the electric field is rho L into A into H divided by 2 epsilon naught and A square plus H square whole to the power 3 by 2 and AN. So what is this AN? AN is unit normal vector from circular ring to point of interest. Circular ring to point of interest. Now, if you want to calculate the electric field at this point, if you want to calculate the electric field at this point P, okay, if you want to calculate the electric field at this point P, so the electric field at point P, the direction will be at point P, the direction will be at point P, AN will be plus AZ, because when you move from Z is equal to 0 to Z is equal to H, this is nothing but Z is equal to H. So when you move from Z is equal to 0 to Z is equal to H, you are moving in the positive direction. It is a unit normal vector from the circular ring to point of interest. When you move from circular ring to point of interest, you are moving in the upward direction, and that direction is the positive Z. So at point P, this AN will be plus AZ, and at point Q, this unit normal vector will be minus Z according to this diagram. So when you move from Z is equal to 0 to Z is equal to minus H, Z is equal to 0 to Z is equal to minus H, it means that you are moving in the negative direction. Z is equal to 0 to Z is equal to minus H, it means you are moving in the negative direction, and if you are moving in the negative direction, the unit normal vector will be minus AZ. Okay, so this is the electric field due to circular ring. Now, the third one is electric field due to circular disc now. So now the disc is placed like this. This is how the disc is placed. So the charges will be present here. In the circular disc, the charges will be present inside the disc. Like this. The charges are present inside the surface. It is now a like surface. Okay. So at point P, if you want to calculate, this is 0, 0 H. Again, it is placed at Z is equal to 0. The radius is R. So now the electric field is E is equal to rho s divided by 2 epsilon naught 1 minus H upon root over H square plus R square and An cap. So the meaning of An is same as we have written in the last discussion. The meaning of An is same. H is the height and R is the radius of the circular disc. Because this circular disc we are defining, so now it is defined by the surface charge density. It is defined by surface charge density. Okay, so the meaning of An is it is the unit normal vector from the conductor to point of interest, from the charge to point of interest. Okay, so the An is the unit normal vector from the charge configuration, that is the circular disc, from the point of from circular disc to point of interest. And rho s is the surface charge density, epsilon naught is constant. So everything we have defined. Why you are having again in the normal direction, that you can understand easily now. If you are having differential surface somewhere here, if you are selecting the differential surface somewhere here, and if you are selecting the differential surface somewhere here, this is the differential surface. Okay, this is the differential surface you are selecting. Because if you want to calculate the electric field, you have to apply this formula, integration over the surface k into rho s into ds divided by r square into ar cap. Okay, so it means that whenever you want to calculate the electric field because of the surface, you should have some differential surface. So that is why we are taking the differential surface which is equal and opposite direction, which is placed in the equal and opposite side. Okay, so because of this, if you want to calculate, the electric field at this point P, so the direction of electric field will be along the line joining, and because of this the electric field will be along this line joining. So when we break it into two parts, that is in the two components, we will be having these two components, like one component is in this direction, another component will be in this direction, and the one component will be in this direction, another will be again in this direction. So again you can see that these components are cancelling each other. So the radial component will cancel each other again, and the direction of electric field at point P will be going in the positive z direction if the point P is lying above the plane. If the point P is lying above the circular disc, then the direction of electric field will be in the positive z direction, and for the downward it is negative z direction. So in this way we have written this formula, and it is derived from this particular expression. It has been derived from this particular expression. Yes. Now the last one, electric field due to infinite charge sheet. Infinite charge sheet. Okay. Now, because of the infinite charge sheet, suppose we are having the charge sheet like this. The charges are present here. This is the infinite charge sheet. And this is the surface charge density rho s. Now, this is x-axis, this is y-axis, this is z-axis. You want to calculate the electric field intensity at point 00 h, which is above the sheet. This infinite sheet is defined by z is equal to 0. Z is equal to 0 plane means xy plane, so that is having the infinite range. So, because of this, the electric field is given by rho s upon 2 epsilon naught and an cap. So it does not depend on the distance at which you are calculating the electric field. It is just lying in the normal direction, and the magnitude is fixed, which is rho s. Rho s is nothing but the surface charge density and divided by 2 epsilon naught. Just you have to focus on the normal component of the electric field. So whenever we want to calculate the electric field at any point P, we have to just focus the normal coordinate. That is, if z is equal to 0, if the plane is placed at z is equal to 0, then you have to focus only to the z coordinate of the point of interest. So we will not be bothering about this x and y, which is 0 or anything. We are just focusing on the value of z, because the infinite sheet is placed at z is equal to 0. You have to focus on the z coordinate. So z is equal to 0, z is equal to h, you are moving in the positive direction, so this unit normal vector will be positive z. If somewhere at any point q, somewhere there at -1, 2 and suppose 5, so you don't bother about this x and y, just focus on the value of z. The value of z is 5. So the sheet is placed in z is equal to 0. The meaning of an is the unit normal vector from the infinite sheet to point of interest. That means from z is equal to 0 to z is equal to 5. When you move from z is equal to 0 to z is equal to 5, the value of z is increasing. If the value of z is increasing, it means you are moving in the positive direction, then the unit normal vector will be positive. And suppose if you want to calculate any point somewhere -2, 4 and -10, Now again you just have to focus on the value of z. So the value of z here is minus 10, and now you are moving from z is equal to 0 to z is equal to minus 10. That means the value of z is decreasing. That means you are moving in the negative direction. So in this case the unit normal vector will be minus az. Okay. So at point R here the unit normal vector will be minus az, and at point Q the unit normal vector will be plus az. Rest of the things are same, which is rho s upon 2 epsilon naught. It doesn't depend on the distance. Okay, so in this way we have finished our electric field intensity and due to the different charge configuration. So now we will discuss in the next class some questions related to the today's topic and also from the previous topic like coordinate system and spherical coordinate system and del operator. So we will solve a few questions tomorrow, and after that we will be discussing the very important topic, that is the Gauss law. Okay, thank you.